Coming up on this edition of the FTC Open Alliance Show, 23513 I.N.T. Robotics is back, and wow, are they building an ambitious, amazing machine for the DECODE season. Custom Swerve, dual intake going on the robot, some really cool stuff with their shooter, and we're going to showcase some testing they're doing as well too, but also some great stuff on the software side, utilizing a turret mode with their sword drive, some more about their sensor implementation, odometry, and just a lot of great stuff we're going to dive into. So check out their progress for the DECODE season coming up here on the FTC Open Alliance Show. Joining us on the FTC Open Alliance Show is 23513 I.N.T. Robotics, coming in out of New York. They have so many cool things to talk about today, and I can't wait to dive right into it. So for a couple of you, welcome back. A couple new people as well, too. Why don't you reintroduce yourselves? Let us know what you do on the team, and we're going to hop right into all the cool stuff you have going on.
Hello, my name is Ellen. I'm in mechanical and electrical.
I'm Tyler, and I'm the lead programmer of I.N.T.
I'm Billy, and I'm the lead mechanical of I.N.T.
Hi, I'm Rachel, and I do mechanical as well as electrical. So to start off, I'll be giving you guys an overview of the master sketch of the robot. So as shown on the screen, this is our master sketch. And we started our master sketch with a side view because that's we figured that's what we're gonna be deciding everything on. So it may be looking a little complicated, but there's actually all important aspects shown. So first is the ramps for the intake/indexer. So there's two main states of the ramp, where the first top state is when the ball is being pushed up into the indexer up here, and the second state is when the ball is being intaked, and so it'll flatten out when the ball is rolling in. So that is the side view, and then these two are our intake rollers. These two are the indexer that changes the path of the ball, and then these two small wheels here are to hold the ball before passing off to the shooter on top, and the rest of the sketches represents the structure. And then after we had the side view, we fleshed out the top view, and the top view here, as you can see, it models all the Swerve modules on each corner, so we can know the space, how much it takes up, and the middle here is how much space the indexer will take up from the side view, and then the rectangle here represents, which is mirrored on both top and bottom because we have intake on both sides, is how much space the intake roller will be taking up. So that is our master sketch, and then all of our mechanisms are based on this master sketch, so everything will be in place as we want to on the master sketch. And then this is our robot, where the intakes are on both sides, and then there's the indexer, and then the entire structure as well as the Swerve. We'll be going into more detail.
Yeah, I was gonna say, I'd love to just hear more about like why you chose this route and stuff. So as we break down each one of these mechanisms, give me a little bit more on like, hey, why do we go this route? Because this is super impressive so far.
We'll be going more into detail on why we have the intake on both sides, but we decide to match the colors of the balls that we thought. We started off with like we should have a storage unit, we should have like an thing that outputs the ball on the other side, but then we might as well have an intake on both sides. So that's how we kind of got to shape of the robot.
Sure.
We'll be going into details now. Okay, so now we'll be going in depth into the Swerve modules. So we decided to go with custom Swerve modules. The main reason why we chose this instead of doing mechanism wheels like the year before is because we realized that while we're scoring, shooting in the zone, we realized that we want to be able to do the X, like crossing the Swerve modules, so that if other robots decide to push us in the scoring zone, we would want to stay in place to have reliable and accurate scoring. And we also debated between whether we want to have two differential Swerve modules or four different in each corner. We stuck to the Swerve module with a motor for the drive and pivot for with a servo in order to have the reliable X across we want. Okay, so to go in with a Swerve module, we looked at many different Swerve modules in the past, including FTC and FRC, and the main aspects that we want to emphasize is that we want to maximize the wheel size in order to have as much contact to the ground as possible. And we try to use all least custom parts as possible. So all the parts are 3D printed or got it from GoBuilder and many other common vendors. And one upgrade that we want to emphasize for the Swerve module is to make sure that it has enough strength push to not get pushed around by other robots and to make sure we have enough torque, which is why we had custom pulleys along with a long wrap around the pulleys with idlers in order to maximize the contact the bell has with the pulley. And next, we want to move on to the drivetrain structure.
And Ellen, if I can ask, were there any major sacrifices that your team had to make going from mechanical to Swerve this year in terms of either packaging or motor usage or anything like that?
Yes, we did. Went through many challenges going with a custom Swerve. Obviously, since it's our first time and first time trying Swerve, we had to also make sure the size fits within the robot. And one challenge was to make sure that we had enough motors and servos for other mechanisms, since it takes up 4 motors and 4 servos. And additionally, we want to make sure that it's as compact as possible so that we have space for other mechanisms. So for instance, in between the drivetrain on the side, so the indexer will be in the middle. In this one corner of the spot, we'll have the telescoping arm climber, which is why we had to have enough space in the middle, which is why it took many iterations. If you see the branches, there's many iterations of different placements of the servos in the middle or the top to arrange all the different components so that it's as minimized and compact as possible. So to move on with the drivetrain structure, since we want the balls to pass from underneath, we had the overall main rectangular structure with the channels and gussets near the top, and they'll be reinforced with many gussets that will be pocketed for lightweightness. And then to move on, next we'll talk about the intake.
Bring me to the intake. So on the screen is the intake we decided on, and right here we also have the intake prototype, which we tried and tested to test the compression and to see if it's actually viable. So the intake was heavily inspired by Vex Robotics, because we saw during Robot in 30 Hours actually that many Vex teams use rubber bands to actually intake wiffle balls, just like we are in this game. So we decided to go for a rubber band, and with testing it, it actually does grab the ball. And a lot of us come from FRC, and one of our favorite FRC teams, Citrus Circuits, they always say, touch it, you own it, right? And this rubber band intake really does accomplish that. And that's what we really like about it the most. And it's also really quick and super efficient.
I love that you're able to take inspiration from multiple different programs too, because you're right. In Vex for pushback, for example, we do see a lot of teams utilizing rubber band intakes and stuff too. So really cool with that. And obviously, Citrus, Touch It, Own It is a fantastic team to take inspiration from. Really cool.
Yeah. And then one last thing to touch on for the intake is that it is on both sides. We wanted to opt for a double-sided intake so we could intake from one side and also push a ball out from the other side. So if we had the wrong artifact code, then we could actually disperse the ball out so we could actually get the right code and we could actually score to get the full code that we need. And that's why there's 2 intakes instead of 1. So now we're going to move on to the indexer that this intake goes to.
Okay, as mentioned before, there's the indexer relies on the ramp on the bottom, and there'll be tensions with surgical tubing, tying all 3 bottom plates together, as well as to the main plate on the top, so that we can reliably have the 2 states of the ramp. And the indexer has many components on it. It will have most of the electrical components, as well as it also has the servos and motor, servos for the intake on both sides. So the ratio is geared up, so it's 4-to-1 for the intake, and the servos are on both sides here and here. We have 2 speeds swift servos on both sides, and then it looked despite both sides being on the same gear ratio, the one side looks a little bit different because of the spacing we had, because of the extra rollers on one side. And then for the rollers that will be holding the ball before going to the shooter is a 1-to-1 with the motor here. And the next we'll be moving on to the shooter.
So next up, we have the shooter that the indexer goes to. Here we have the prototype of the video that will be playing on screen right now. This is the prototype that we have for the shooter that intakes the balls with these green wheels, right? and then it goes up into our hooded shooter, and it is adjustable up here with this servo that changes the final tangent of the arc of the ball to actually change the course of the ball. So we landed on this shooter design after testing a double wheeled one that mainly applies backspin, and we realized that we don't have much control over the ball, so we wouldn't be able to score from, let's say, the farthest triangle and from the closest triangle. So we wanted to go for an adjustable hood. And the best thing about this is we currently there is no yoga mat on it because we took it off to make our next shooter, which is going to be a more iterated version. But the yoga mat applies compression throughout the whole way of the hood, and that means that your motor loses less when you actually end up shooting the ball, because now you're adding compression from the yoga mat and not just your wheel. So your motor has less recovery time now that you put this yoga mat on the back. And our next shooter is going to be heavily taking inspiration from the 2022 game Rapid Reacts. We would like to have a fully adjustable hood with wheels on the top that also spin. So now we're not only adjusting the hood, but we're also adding power to it. So we're giving it the backspin that we want, so it's not going to fall out of the place that we're scoring, and then that will also give it more power and strength. And yeah, pretty much.
If I can ask
That's
real quick
about
on the shooter there, can we bring that back up on screen real quick, that prototype that you have?
Yeah.
So Billy, looking at that, where is the adjustable part happening? Is it just that little flap on top that you have, or is there like a whole part that adjusts?
Yeah, this flap is ran by a servo, right? And it simply goes up and down, and it just changes the final arc. And it's really effective for what we wanted to do, because we didn't want to pivot the whole hood at first, but we decided that in order to pivot the entire hood, if we want a wheel to be running at the end of the hood, we would also have to pivot the whole hood. So that's how we ended up with the new design that is currently being worked on.
No, I'm delighted that you all went that way. I think so many teams are trying to be a little too overly complex sometimes with an adjustable hood, and I think the way that you're approaching it is a great way to go about that too. So I'm glad we were able to showcase that a bit more. Cool stuff, guys.
Oh, okay. So now we are going to move on to the final mechanism, the climber. So Swerve has done a really good job with designing a really hard climb this year, and it took a lot of thinking to come to our current solution that we came to. The first solution was originally going to be this scissor lift idea that we had to climb over the other robot and then be able to drive over them. But then we realized the biggest hindrance of this design would be that you wouldn't be able to climb over an 18 by 18 inch robot. So that's how we got to the new current design. So the new climber design will be using, shout out Offset, we're going to be using their telescoping arm to push up, and then we're going to be pushing up on pretty much an aluminum plate, right? And then on that aluminum plate, there's going to be a seesaw mechanism, right? And the seesaw will be held up slightly with torsion springers, even surgical tubing. So it's slightly held up at an angle, so to speak. So we have the plate that you're climbing on, which is flat, and then you have an angled plate. So now the robot, our alliance, can drive onto us, right? And then they're going to drive on, and then they're going to hit the point where the seesaw is, and then they're going to tip over, right? And now with this tip, we could fit an 18 by 18 inch robot despite the telescoping arm being on the inside, because now their robot's in the air. So we could lift them into our perimeter by using the angle of the ramp that they're climbing on. And that's how the whole climb is going to work. So
originally your team was looking at doing like a scissor lift, if I remember correctly, right? Looking on your OA block.
Yeah,
so what made you change from going scissor to this design instead?
So the reason why we just changed from the scissor lift to the telescoping arm was not only because we wouldn't be able to climb over an 18 by 18 inch robot, but also the idea of speed, right? Scissor lifts are not really the fastest thing, right? But telescoping arms are known to be pretty fast. And there was also another problem being the motors that we had to use, right? Due to the amount of motors that the Swerve uses, the limitations of the Axon, the servos on the Swerve too, we had to try and limit our motor usage everywhere else. So we ended up with one motor to climb, right? And the telescoping arm fit that need perfectly, because then that whole actuation of the arm going up is just one motor only. So that's how we ended up switching from the scissor lift idea to this. And it also makes us more adaptable with the ramp again, because when you think about it, there might be a lot of 18 by 18 inch robots, and we're relying, if we go with the scissor lift idea, we're relying on them being smaller than us instead of designing to overcome their 18 by 18 inch. And we decided that it would be better to design to overcome that problem as opposed to being able to simply climb over them at the end. And that's how we landed on the new design.
I mean, overall, this robot design is so cool so far, and I can't wait to keep seeing that progress. But we got a lot of great stuff in software that we want to cover as well, too. What are some things that you want to highlight from that aspect and give us some updates on?
Yeah, so they talked about a lot of mechanisms. It's definitely a lot to code, a lot for the robot to do.
Lucky
so
you.
I'll start on the Swerve. Yeah, I get to have a lot of fun. The Swerve has 4 drive motors and has 4 turning servos. And it has 2 encoders on each module, one for the turning and one for the driving, which would allow us to have odometry for the Swerve drive. And basically what we did to actually code the Swerve drive, because FTC doesn't have all that many libraries for it, is coming from FRC, like Billy said, we imported WPIlib into FTC code. And so the hope is that we can use a lot of the Swerve math that WPIlib already utilizes in FRC, like Swerve kinematics and all of the other math, to actually code the Swerve drive in FTC. And don't have the Swerve drive to test it out yet, but the hope is that even with the difference in motors and whatnot, it'll still work out. For the indexer, we started out trying to have as few sensors as possible for the artifacts. We tried out a bunch of positions, one in the middle, having 2 on each end of the indexer, and such. But in the end, we settled on just having 4 sensors, 1 in each compartment. And the reasoning behind this is, even though we have more color sensors for our indexer, it's a lot of a safer approach for example, if one of our sensors breaks in the middle of a match or gets disconnected or a ball gets stuck or for whatever other reason, that we have another 3 like backup color sensors that we can fall back on, and for the driver to be able to still be able to use the bot even if we have a piece stuck or something like that. For our turret mode, so instead of having an actual turret on the robot, since we have Swerve, what we decided to do is we can have a turret mode where the robot locks on to our target using a limelight, and just looking at the April tag, we can essentially make the robot into a turret where it always looks at our scoring zone, and whenever we intake a ball, it'll immediately shoot it out and score. So we're also trying for shooting while moving accurately, of course, during the game to maximize our scoring output without having to worry about our pattern or the colors of the artifacts.
From to ask you, from the shooting while scoring sort of thing, have you kind of like mapped that out? What what during a match that actually would look like? Because you think about like from an accuracy standpoint, you're right. Because if you get bumped by another team or things move, do you think it would be better off just to stay put and fire your shots really quickly? Or I guess what's the main advantage to shooting while moving at the same time in that aspect?
Yeah, well, the thing is, turret mode is only really a mode that the driver can choose to turn on or off depending on, how the opponent is playing. If the opponent's playing more defense, maybe they won't have it on. But if the opponent's just focusing on cycling themselves, our thought is that during the game, there would be a lot of artifacts on the field. And with this turret mode, that would lock the angle to the scoring zone, which would reduce the amount of control the driver has over the robot. It would also increase our scoring drastically if we're able to shoot while moving and, in our mind, be constantly intaking artifacts.
And another thing on the turret mode and the defense idea in the match, that's another reason why we ended up landing on the Swerve, due to the usage of X mode. If we go into X mode while we're shooting, then it's going to be really hard for another robot to push us out of the way while we're shooting. So we're going to have a very stable shot, which is another big reason as to why we went with Swerve in the first place, because we knew that defense might be pretty prevalent in this game. And Mechanim is very prone to being pushed around, but Swerve, even when you're not in X mode, it's going to be very hard to push on Mechanim. And when you're in X mode, it's hard to push even with another Swerve, as seen in FRC. So that's really why we came to this conclusion of the Swerve modules too.
I'm glad you guys thought all that through. That totally makes sense to me. Anything else you guys want to highlight or cover on your robot or progress at all?
We have our updates on the Open Alliance on Chief Delphi, so we'll make further posts based on our prototypes and versions for Swerve. So check that out if you guys are interested.
Yeah, under 23513 I.N.T Robotics, you can check that out right on Chief Delphi as well too. So some great updates there, and we look forward to more from you as well too. Anything else that you want to share or talk about?
Oh, thank you, Offset, for sponsoring us.
Yeah, thank you so much.
We love the telescoping arm.
So we wish 23513 I.N.T Robotics, thank you so much for telling us more about that. I mean, what awesome progress you all are making. I think even last year I go back and I think about a lot of cool, ambitious stuff from your team, and I can't wait to see it come to fruition. And I know your team's going to do a great job with that. So best of luck the rest of the way through, and make sure you keep an eye out on their build blog as they continue their season. Good luck, everybody.
Thank you so much.
Thank you.